GANs as feature extractors that you learn in an unsupervised fashion on unlabeled data. And then lastly, I have one slide to basically tell you what I want to do next with these methods. So to start off with, a quick introduction to generative models itself, not in general, but just in the context of this talk. Let's think of a generator as some black box that basically just keeps generating images. And you could ask, let's say you have a generator that generates images from the real world, like basically all the images that you see on Flickr, for example. And this is just a black box that is somehow learned or is just hard-coded by some magical person. So to go a little further in a different direction, so you can think of the generator now as being some probability distribution that you learn, some function which takes in some latent variable z, and then it will generate an image. And here, if you think of z as a scalar, if you go left in the range of z, it starts generating dogs. If you go right, it starts generating cats. That's just an example of how you can think of generative models with latent variables. So that was a very simple example there. Usually what we do is z is usually some kind of multivariate Gaussian or like some multivariate distribution that's fairly complicated. And that goes in to the generator, and the generator produces a corresponding image. And depending on how you change the z there, different kinds of images start to appear. And to take this one step closer to adversarial networks, the generator here can be a neural network that can be trained just via standard gradient descent. One simple way to train such a network is, say, you have some inputs, latent space z, that goes into a neural network, and then you have a data set of real images, let's say the ImageNet database, for example, and then you can have some cost function that measures whether a generated image is close to a real image, and then do a gradient descent back and train a neural network, and now you will have a neural network that starts generating images. If you do it just with this setting where the image then goes into a simple non-parametric cost function, what you will get is just blurry images. Like what you will learn is a generator that optimizes some kind of KL divergence and converges to the mean of all images, which is usually nonsensical. So an interesting way to address this problem was proposed by Ian Goodfellow and his colleagues at Montreal Institute of Learning Algorithms at that time in 2014. What they do is they propose an interesting variation where your generator here is still exactly as I described before, but then you also have a discriminator, which is also a neural network, that when you send in generated samples into the discriminator, the cost of the task of the discriminator here is to classify whether the images come from the real distribution of images, that is like ground truth, or from these generator samples from the generator itself. So the discriminator's optimization is essentially, it takes some samples that are either real or from the generator, and it has to classify them accurately. So you can, so just describing that in a slightly different diagram, because I had these diagrams lying around and I wanted to reuse them. So it's the same thing. You have a generator that produces a sample. You want to classify whether it's real or fake. You get a discriminator. And you can think of the discriminator as a parametric learned cost function for this whole task. Because having a good cost function that tells you whether the image comes from a real space of images or some fake distribution is really hard. It's like you can't just put like a mean square error or some pixel-wise log likelihood and accurately describe this complicated distribution that you're trying to capture. So you can think of the discriminator here that we're going to learn as a parametric cost function that you are learning in the process. And the way that these things are trained is just via standard gradient descent. At the end, you have a classification loss of whether the image is real or fake, and then you have a standard backdrop that is used in neural networks to learn each parameter of your system. And when the discriminator is being trained, when the generator is being trained, the generator is being trained to full D, the discriminator, which means that the generator is being trained with the same classification loss, but with inverse labels. That is, if the generated labels are given, the generated images are given a real label, and the real images are given a fake label. And you just have a standard classification loss, and that's how the generator is trained. And when the discriminator is trained, it is doing the exact opposite. It's doing the standard classification loss, where it wants to classify accurately that the generated images are fake images, and real images that you give from your training set are the real images. And the training is typically done in an alternating loop. You show one mini batch of real images, one mini batch of generated images, and so on. One interesting theoretical property of generative adversarial networks is that if you have an optimal discriminator, you can show that this whole process actually optimizes the Jensen-Shannon divergence, which is a bit more relaxed to modeling multimodal distributions than the KL divergence metric, which basically is really biased towards capturing more of the mean density than capturing multiple modes. This was published in mid-2014, and it was presented at NIPS 2014, and the samples of this network where you have an image generator look like this. They look very blurry, very noisy, and not very good. But these samples at that time really captured a wide audience because at that time this was the best we could do in building generative models of images. So after that, me and my colleagues from Facebook and NYU, we published a paper that extends the generative adversarial network in two ways. One, instead of having one single black box of generator that generates from the latent space all the way to, say, a 32 by 32 pixel image, we instead break it down into a Laplacian pyramid setting where we have separate generators that go from 1 pixel to 4 pixel images and 4 pixel to 8 pixel images and so on. So the problem becomes slightly easier to model in general. And the second modification we do is, apart from giving just the noise, that is the multivariate Gaussian to the generator, we also give a one-hot coding of the class we want to generate. And this is not in an unsupervised setting. You have the ground truth class of the images that you're trying to generate, and you just inject that class as well into your generator, and you hope that the generator will start to use this information of the information that you give about the class that is trying to be generated to automatically start learning a generative model that, depending on the class that you tweak that is an input to the generator, it starts producing those particular samples. As an example here, when we trained it on the CIFAR data set, depending on which one-hot coding we gave to the generator, apart from the noise variable, it would generate that particular class of samples. And this started to look much better than Goodfellow's original paper of generative adversarial networks. So after that, some of my colleagues, and in parallel there were several research projects going on adversarial networks. One of them was my colleagues at Facebook Guided Research, Yang Kun, Michael Matthew, and Camille Kukri. They were doing video prediction. That is, you take 3 or 4 frames of video from the past, and you want to predict the 5th and 6th frames. And this is of interest from like a planning and robotics perspective. I'll come to that in my last slide. So in the video prediction setting, what they did was they took the standard generative adversarial network framework. They tried to apply it to video prediction, and it didn't work as well. It would generate stuff, but it would mostly look nonsensical. So what they did is they went towards a hybrid architecture, where they also had a mean square error loss with the ground truth of the videos you have, and also have an adversarial loss on the side. So this is kind of some kind of hybrid loss where you want to converge to whatever your ground truth roughly gave, but also wanted samples that didn't look just like the mean of all possibilities. And one picture showing a few results. You can look at more results in the paper. But if you see, these are the input frames, the 4 input frames to the network. This is the ground truth on what happens next. If you just use an L2 loss purely, it starts giving really blurry predictions. If you have an L1 as well, it gives weird blurry predictions. If you have an adversarial or an adversarial with this hybrid loss, it gives short predictions, also minimizing the signal-to-noise ratio of what happens in the future. That was a really interesting direction that they took. And then we parallelly published a paper. I call this the pretty picture GANs paper because it was a very empirical paper. So one problem with generative adversarial networks that I haven't told you yet is that they're really hard to train. They often collapse, which means that they just produce nonsensical garbage. They never start learning to produce samples from the distribution that you're trying to model. So we started empirically looking at why these networks collapse with certain types of architecture and don't collapse with certain types of architectures. And we found a class of architectures that adversarial networks are really stable to. We call these DC GANs, and they kind of look like this. They don't have any explicit pooling layers. You have strided convolutions with batch normalization and ReLUs, and that's about it. Very simple structures. And they started producing really pretty images that everyone was like really thrilled by. But apart from that, they actually had a real practical application. We showed that you can use the feature representations of the neural networks that you learn in the generator and the discriminator as feature extractors to do other tasks, like say classification tasks. And one small table showing our results is there's a data set called Street View House Numbers. It's used all the time in computer vision, where you have about 500,000 or 700,000 images of pictures from Google's Street View car of digits, house digits. And the problem here is classifying these digits into 10 labels. 0 to 9 numbers, and if you have there are several experiments on this data set where you use this large data set of 500,000 samples as an unsupervised unlabeled data set to build unsupervised models, and then you limit the number of labels with supervision, you limit the number of labels you give to, let's say, 1,000 labels, and then you see what kind of classification error you get. And there were other methods at the time of publication that got pretty good, like 23% error rate on 10 label classification problem, just using 1,000 labels of your data set. And with the DC GAN architecture, we trained a DC GAN on the Street View House Numbers data set of unlabeled data, and then from a separate validation set with just 1,000 labels, we just quickly, from a separate set, we trained the network just on 1,000 labels, and then we checked the error on the validation set of this data set, and it got 22% error rate, which seemed pretty good at that time. I will show you some more semi-supervised results from other papers in a second. Another interesting thing that we did in our paper, also empirical, is that this latent space that you learn, it's just like a multivariate Gaussian latent space, and we didn't actually ask the network to learn any semantic properties of the input distribution. Yet it actually starts having interesting arithmetic properties in this latent space. As an example, we built a phase generating phase generator, and we took samples from the latent space with specific semantic properties and did arithmetic on them. Basically, take the z noise vector of the first sample, subtract the z vector of the second sample, and then add the z vector of the third sample. And if we did this weird, interesting arithmetic, the resulting generation would actually hold in semantic structure of what you would expect as, like, when you look at these three samples and the arithmetic, you would expect that the man would be removed and a woman is added, so a man with glasses would come out, and a woman with glasses would come out, and that's kind of what you expect. And this is not just like a pretty result I'm showing for the paper or for the talk. There's a live demo where results like these largely hold whatever you throw at them. And next I want to show a paper from Berkeley, from Alicia Efros, Trevor Darrell, and his PhD students and postdocs, where they applied adversarial networks for inpainting. And inpainting is, I guess everyone here is familiar with inpainting, but so they take out a patch of the original image from the center of the image, and they want the neural network now, or some system, to fill that patch. And if you and like the adversarial laws really helped the adversarial laws really helped in giving non-blurry inpainted results. As an example, here's the input with emptied out the center. This is what a human artist drew. This is what the L2 loss-based context encoder gave them. This is one with the hybrid L2 plus adversarial loss encoder gave them. The adversarial plus L2 hybrid loss is sharper, and it gives you plausible inpaintings. And next, I want to talk a little bit about the input Z that we get, that we give to the generator when you're training these adversarial networks. Usually, it's a multivariate Gaussian, and it's very hard to disentangle this latent space into some explainable latent factors. And that was something of interest for several research groups, including us. And what we wanted to do was, without actually, if you remember what I said about the class conditional GANs, we would give explicit classes that need to be generated. But instead, what we wanted to do was, in a completely unsupervised way, just give some multivariate Gaussians and some categorical distributions as input, and see if the generator would automatically disentangle certain semantic properties into these latent variables. And and what happened? The OpenAI guys, John Shulman, Illicit Discoverer, C-Chan, they figured out how to do this well, where they would give several categorical distributions and several multivariate Gaussians as input to the generator, train this whole thing in an adversarial setting. And what's interesting is that even though this is completely unsupervised, unlabeled, right? They change each of these categorical variables during generation time to see what they're capturing, and see that if they change one of the categorical variables, it actually disentangles into each of the 10 digits. That is, like, depending on which one-hot encoding you give to the input of the generator, it produces a particular digit. And another variable does rotation, another variable does width, and this is completely unsupervised and just naturally occurring with this adversarial training, where you give categorical and multivariate Gaussians as input. The trick they did in this paper was that, so what used to happen if you did train this naively is the generator would usually just ignore the categorical distribution entirely and just use the multivariate Gaussian to basically generate samples. So what they did is they had a regularizer that would force the network, the generated network, to use both distributions, and it would penalize the network if it didn't use one of the inputs that it was getting. And another sample here is they did a continuous variation of this on a 3D data set, and the network automatically figured out latent variables for rotation and the width of the furniture and so on. To take a second to explain why all of this is probably maybe useful, it's that we often have a lot of unlabeled data that we will get labeled by mechanical Turk over like a lot of time and taking a lot of money, and instead we would want to just train unsupervised algorithms that would learn a good representations on this unlabeled data, and instead just get like say 1,000 labels of your input of your data by some grad student, and that would be sufficient. And so last paper I want to discuss, also from OpenAI, that appeared recently. It's I explained earlier that unsupervised learning, adversarial networks are very unstable to train, and there's also a semi-supervised learning story we are trying to put around the adversarial networks. And this paper tries to address both of them. DC GANs address the stability issue to a large extent, but there are issues with GANs when you go to like a higher resolution than say 64 by 64 pixel generations, for example. And so there's still stability issues with training GANs, and so this paper proposes that we do four kinds of regularization to training GANs that would help the stability of training GANs a lot. The first one is feature matching, which just says that instead of having a single loss at the end of your discriminator, you start matching the statistics of the intermediate layers of your neural network among the real samples and the generated samples. So it's a regularizer that tries to push more information through the network, and that seems to work really well. Another thing is mini batch discrimination, which is that instead of classifying each sample as real or fake, you take a mini batch of samples and you classify the whole mini batch as real or fake. The third one is label smoothing, which is simply instead of having a ground truth label that says 0 for fake samples and 1 for real samples, you jitter the labels a little bit, saying if it's a fake sample, I'll give it to be between like some random number between 0 and 0.2. And if it's a real sample, it'll be some random number between 0.8 and 1.0. So it's just like the label smoothing exercise there. And all right, so I'll show some semi-supervised results from this paper, which are really, really interesting. Earlier I showed our SVHN results on the DC GAN paper, which were about 22% error with 1,000 samples. And these guys took it to a whole other level where the error is gotten down to just 5.8% in a completely unsupervised, using a completely unsupervised GAN, except for 1,000 labels that are given to train this classifier. And that's pretty good. One of my original papers from 2012 that applied ConNets on this data set in a completely supervised fashion using 700,000 labels actually had 5.1% error. So it's just interesting that in a completely unsupervised setting, with very limited supervised labels, we're getting to a state which is very interesting practically as well. Another example is this data set of Cypher 10. They also have good results. Just with 1,000 samples, you get to 20% error on the Cypher 10 data set. Last slide, what's next? So the reason we've been pursuing GANs, also unsupervised models in general, one of the most interesting things for us, at least for me as a researcher, is that when we are trying to, in the real world, when we plan any task, when we do any action, voluntary or involuntary, we plan all of this in our head. If I want to go out, get some coffee, I already mapped in my head that I have to open the door, go there, open the door, avoid these tables, and so on. And this happens very naturally. We have an internal model of the world in our head. Essentially, we have a generative model of the world in our head that, given some frames of the past and some action that you want to take, it kind of predicts what happens. And I see this as something really, really, something that's really needed for in the setting of robotics, general AI agents that we want to build, smarter machines which adapt with really little data, that start building internal models of the world at large that they're trying to reason with. So, gonna be exploring more research in that direction. And now you guys can ask me questions.
Is there any theoretical understanding of why not GANs converge when you train them?
So we are actively looking into the theoretical properties of GANs, the training dynamics as well, like what is the stable state of GANs? Why are they in this weird state of chaos, and why they don't train in certain settings? But at the moment, there aren't any papers that are published yet. But that's a very important question that we're actively looking at.
Could you comment on the inherent dimensionality of this problem? So the images appear very, very highly dimensional, a lot of pixels, the video is even more because we put the time, but at the end of the day, there's a limited number of things that can happen in the real world. So do you get any feel regarding how many dimensions we are really working with? And perhaps this Gaussian mixtures, this Gaussian model tells you something. So how many dimensions we need to?
I would say it's just like the number of dimensions that we're working with is probably an intractable number by default. But what would be interesting is to build a hierarchy of latent variables, which makes the problem more tractable. Where it doesn't matter if you have a ridiculous number of dimensions, you're trying to build this hierarchical representation that can just capture everything that you're trying to do. I don't have an answer on how many dimensions we...
But when you stimulate your model, right, you have an input distribution.
So in general, in our models, we use 100-dimensional multivariate Gaussian or something like that, or 200.
And it was sufficient to generate rise if you look at it.
It's sufficient to generate in a limited setting, for example, like a bedroom generator or like a face generator. I mean, faces can be generated with 40 or 50 dimensions in general, right? So yeah, in a limited setting, it's enough, but in a generalist setting where you want to generate any possible thing, I think that's probably not sufficient.
So what kind of, will the generator move outside of the kind of implicit constraints that was learned? I mean, say you have a bedroom generator. Mm-hmm. It's going to have seen examples where the bed's on the right side of the room, the left side of the room's on the middle, but it won't go to the lengths of having the bed floating off the floor or any of those kind of things, right?
Well, if the bed's floating on up in the air, then that's not coming from the real distribution of images anyway. So, and I haven't seen anything that was generated in that weird. There is actually some examples where generations of humans sometimes have 3 eyes. But that's because of the way we send in the. I think that's because of the way it is like the networks are constructed. These are convolutional nets.
You lose some of the local files.
Yeah.
And I guess that's the importance then in having the discriminator, right? I mean,
Yeah.
they'll look at that and say, okay, that's really not a realistic human because they have 3 eyes.
Yeah, the discriminator, without any loss in spatial resolution, can start to discriminate certain features, then that would basically be eliminated.
So in that case then, does that mean that you're going to only be able to really generate examples that you've somewhat already seen in your training set of your discriminator?
So usually we do checks to make sure that the generator is not copying anything from the training set. The kind of checks we do is L2 distance in both pixel space, feature space, with like all kinds of jitters to make sure that it's not doing some kind of non-trivial thing. But we also do interpolations between 2 generations to make sure that all the generations in between these 2 generations are also like valid generations. And beyond that, I don't think we can do much better than that. And these are not robust checks. But like the semi-supervised story is the most compelling thing, where what are we trying to do? Are we trying to actually generate from the real distribution, or are we just trying to learn good representations?
I think part of the problem is to actually make sure we don't have the whole in this distribution from which we generate.
Yeah.
Because I think we should have another adversarial to checking for tops. Because what we check, whether it's realistic, that there may be some parts of the distribution we never actually generate samples from.
That's actually a good idea. I think if you guys work on that, that'll be like an interesting direction.
Yeah. Well, we haven't been working before we ask the question, but maybe now we should.
Cool. If there are no more questions, we'll wrap up there. Thanks, Samim.